What's up, everybody, and welcome to a little bit of a chemistry video on the states of matter. We're actually going to be doing 5 videos based on the states of matter. You can find them in your book in Chapter 12, Sections 2 through 4, and then a little bit of Chapter 15, Section 1 as well. Today we are going to start with the first one, where we are going to look at forces that are between different molecules. These are called intermolecular forces instead of intramolecular forces, which are forces inside molecules like bonds. These are not bonds. But I don't want to give everything away on this first slide, so let's move on. So, intermolecular forces. All right, all right, these hold molecules together. They hold a grouping of molecules together. They are between molecules. They are not bonds. All right, they get the symbol IMF from the I in inter, the M in molecular, and the F in forces. And so most of the time you're going to see me refer to them as IMFs because it's a lot easier to say and not as big of a mouthful as intermolecular force. So IMFs hold different molecules together, or hold the molecules together. All right, if you have like 2 molecules, they are going to get stuck together through these IMFs. They are effective only over short distances, so the molecules have to be pretty close to each other. And again, like everything that we've been talking about in bonding, this all has to do with electrons being attracted to protons, but this is one molecule's electrons being attracted to the other molecule's protons. All right? And sometimes we call these van der Waals forces based on the scientists who kind of first started doing all the work on these things. You're not really going to ever hear me say the name van der Waals forces. I like to call them IMFs because it's just the easiest of things to say. The first of these forces are known as dispersion forces, or sometimes called London forces, or every once in a while known as London dispersion forces. These are found in all molecules, all right? All molecules have London dispersion forces. They are the weakest of the IMFs, all right? And they result from weak momentary dipoles. So, as you know, electrons are zooming all over the atom. Every once in a while, just statistically speaking, there might be more on one side of a molecule than the other side of the molecule. And that would cause the side with slightly more electrons to have a little bit of a negative charge. And if the same thing happens to the next molecule over, but in the opposite way, so that all the electrons are on one side, there's also the side that doesn't have that little bit of negative charge, has a little bit of a positive charge, and a negative and a positive will get attracted to each other. The important thing about this is they are found in all molecules, and they cause nonpolar molecules. Remember, nonpolar molecules, all right, have equally distributed electrons. All right, it causes these nonpolar molecules to be liquids or solids and gives something holding them together. All right, a lot of nonpolar molecules are gases. The ones that are liquids and solids occur because they have these London dispersion forces. All right, these are also the weakest intermolecular forces. The next group of forces are the dipole forces. They occur between 2 polar molecules, and I have a couple examples right here to draw for you because it's kind of easy to see this when we draw these diagrams out. So I'm going to start with CH2O. What we have is we have a carbon singly bonded to two H's with a double bond to an oxygen. That oxygen has a couple lone pairs. Looking at this right away, there is not an equal distribution of electrons. All right, there are more electrons over around that oxygen atom than there are by the hydrogens because of those lone pairs, and this is going to make that part with the oxygen atom have a slight negative charge. We use a lowercase Greek delta to mean slight charge, but it's slightly negative at this end of the molecule, which means the opposite end has a slight positive charge. And if this happens on two neighboring molecules, they will arrange themselves in a way that the slight negative and the slight positive the slight negative on one and the slight positive on another one will kind of join up. It's easier to see in a smaller molecule and a simpler molecule like HCl, so let's draw that. We have an H singly bonded to a Cl. There are 6 unbonded lone pairs, or 3 lone pairs, 6 unbonded electrons on the chlorine, and so the chlorine has a lot of electrons, which means it's kind of negative. So we'll put in that weird little lowercase delta symbol with a negative charge. The other end of this molecule, where the hydrogen is, doesn't have the electrons, so it's going to be a little bit more positive. Positive part of this molecule. So it's got a slight positive charge. And if we have several of these molecules in the same area, they are going to arrange themselves in a way where a negative chlorine from one molecule is going to be attracted to the positive hydrogen on another. And a positive hydrogen on a molecule is going to be attracted to the negative chlorine part on another, and I'll draw these in here. I'll shade the negatives in red, the positives in blue. So this chlorine here is going to be, these chlorines are going to have like slight negative charges, and so we can kind of then also put in the slight positive charges that we would see on the hydrogens. All right, we can write in the weird little delta as well for the positives and the negatives. So there's the slight positives. And now here are the slight negatives on the 2 other Cls. And what you'll notice is we have a slight negative and a slight positive right by each other right here. And so there will be an attraction called a dipole force between them. And we'll see the same thing over here with the other 2. And if there were more samples of HCl around, more molecules of that, this one would probably have some kind of dipole force. And so with this one, where they would be matched up with other molecules, right? And so these green dashed lines are the dipole forces, and any polar molecules show these. But the real big intermolecular forces, the strongest intermolecular forces, are the hydrogen bonds. And you talked about these in bio a little bit. Hydrogen bonds are not real bonds. They're not as strong as ionic bonds or covalent bonds. But they still use the word bond, although they are an attraction between molecules and not an attraction between atoms. These are IMFs, all right? This is a place where chemists figured we'll call them bonds and confuse the non-chemist people because we know that they like to do that. It is a type of a dipole-dipole attraction, but it's a very special type of dipole-dipole, and it only happens when hydrogen is bonded to nitrogen, oxygen, or fluorine. Only hydrogen to nitrogen, hydrogen, oxygen, hydrogen to fluorine, HN, HO, or HF bond has to be present in order for hydrogen bonds to occur. And the hydrogen from one molecule is attracted to the lone pairs of the other molecule, which is, the electronegative part, which is the N, O, or F elements. And we'll see an example of this in a second. The biggest example of hydrogen bonds, sometimes called H bonds, is in water. What we can see here in this diagram, all right, the red ball thing is oxygen, the gray ball things are the hydrogens. All right, the oxygen has a slight negative charge on it. All right, and that slight negative charge of the oxygen is attracted to slightly positive charges on hydrogens of other water molecules. Now, this causes a couple of weird things. All right, this causes ice. Ice forms as there are more intermolecular forces, more hydrogen bonds, and hydrogen bonds are strongest at a certain length. And so when water freezes, these hydrogen bonds actually push the molecules a little farther apart than you would expect, and so ice expands. And when ice melts, this lattice of hydrogen bonds collapse and the molecules move closer together again. But there are still hydrogen bonds in liquid water. They're just not as strong or as numerous as that we see them in solid water or ice. So if I took a look at some practice here, all right, and I wanted to identify all the IMFs present in all of these, well, the first thing I can do is I can write down the London dispersion forces, because everything has London forces. So I'm going to go in and write that down for all of them. All right. Then sometimes it helps to draw a little picture. All right. H2O we just saw on the last page, and it should be easy because we've used it as an example. H2O looks like this. All right. Obviously, what we got going on here is the oxygen is a negative end. The hydrogens are kind of like slightly positive ends. So because of that, we have a dipole, a thing with a negative end and a positive end. So this has dipole forces as well. And also, because we have hydrogen bonded to oxygen in dipole forces, these hydrogen-oxygen bonds that are in here, this H2O, water, also has hydrogen bonds, or H bonds. All right, let's look at the other one. We have got nitrogen gas. Nitrogen gas is just diatomic nitrogen. It's a nitrogen triply bonded to another nitrogen. Well, there's no polar bond to begin with because you got two nitrogens bonded together, and all the electrons are equally distributed. It is non-polar. All right, which means the only forces that are there are those London forces. And we're all done. Dichloromethane, CH2Cl2, is a fun little compound. It looks HCl, and the Cls each have 6 dots. All right, if we look at this, the Cls have a lot of electrons. They're slightly negative. The H's have like no electrons, so they're slightly positive. What we have is we have a polar molecule. And so if we have a polar molecule, we have the dipole force as well. All right. What we do not have is we do not have hydrogen bonds because our hydrogens are bonded to carbon. And remember, for hydrogen bonds, you have to have hydrogen nitrogen, hydrogen oxygen, hydrogen fluorine. We don't have that, so it's just London and dipole. The fourth one, we've already seen this this shape, this compound drawn out earlier in this lecture, but we'll draw it again. We got a carbon, was double bonded to an oxygen, which had 4 dots. And then that carbon was single bonded to 2 hydrogens. And if we take a look at this one, right, again, over here, the oxygen, lots of valence electrons, lots of electrons, unequal electrons. So it's kind of negative. The hydrogens are kind of positive. It is polar. And if something is polar, it has those dipole forces. All right? Notice it's dipole, not dipole. It's not a dipole force, it's a dipole force, although some of you are now going to call it dipole, and you'll get a little chuckle for saying dipole, which is why I brought up dipole. But it's a dipole force. All right? Are there hydrogen bonds in this? You might be tempted to say yes because there's hydrogens and oxygens, but those hydrogens are not bonded to the oxygen, so there's no H bonds. You need the direct bonding between the hydrogen and oxygen to fully appreciate, to fully have hydrogen bonds. They have to be there. That bond of hydrogen oxygen has to be there. Right? That is it on these IMFs. The thing you mainly do is go in, take a look at a molecule, figure out what IMFs are in it. Every molecule has the London dispersion forces. Every single one always London dispersion forces. Every polar molecule has dipole. And then if you have hydrogen-oxygen, hydrogen-nitrogen, or hydrogen-fluorine bonds, then you can have hydrogen bonding going on as an IMF as well. All right, the rest of the work that goes along with this is all about these different IMFs and what are in different molecules. If you have any questions, you get a hold of your teacher. You should know how to do that. We like to answer questions on this stuff because we are teachers and that's what we do. Thank you and have a good one.